as one of the post office's best customers, we're only too well aware that the cost of postage depends on the weight of the letter that you want to post. When we recorded this program, if you wanted to send an ordinary letter by first-class post, it would cost you 8.5 pence. But if the letter weighs more than about 60 grams, then it'll cost you more. For example, this one, if I put it on the scales, I see it weighs about 120 grams, and so if I want to send it by first-class post, it will cost me 15 pence. This idea of the cost of postage depending on the weight of the package is an example of one of the most basic ideas in mathematics, the notion of function. We're going to use the word function in a similar sense to the everyday context, but because of the way we want to use it in mathematics, we have to be far more precise as to the way we define function itself. But before we get to the definition, let's have a look at a couple more examples. Do you remember the work we did in Unit 3 on rotations? One of the things we worked out there was the height of this point above a horizontal axis. If this length is just 1, then this height depends on that angle, and in fact it's given by sine of the angle. Change the angle, and you change this height. The height depends on the angle. Height is a function of the angle. For example, if the angle were pi by 2, this height would just be 1. Let's have a look at another example. These represent thermometers. This one is in the traditional Fahrenheit scale, and this one in centigrade. With Fahrenheit, the freezing point of water is 32, and the boiling point of water is 212. And in the centigrade scale, the freezing point of water is 0, the boiling point is 100. So a reading of 0 on this scale corresponds to a reading of 32 over here. A reading of 100 there corresponds to a reading of 212 back here. Now, as the temperature varies, the readings on these scales must vary. So if it's a different reading on the Fahrenheit scale, there must be a different reading on the centigrade scale. And in that sense, the centigrade reading depends on the Fahrenheit reading. So in all three examples, we've got this notion of dependence, one thing depending upon another. And to make that idea of dependence far more precise, here's Roger Duke.
I like to think of a function as something actually functioning, rather like factory functions. We feed in raw materials and out comes some sort of end product, the result of a processing performed by the function. If we take, for example, the function representing the cost of posting a letter, then we can think of this as a factory and represented by this box. We have an input and an output. What we feed in is the weight of a letter, and what comes out is the cost of postage. If a letter weighs 50 grams, the function processes that weight to tell us that the cost is 8.5 pence. 120 grams becomes 15 pence. $240 grams becomes 22 pence, and so on. We can use the same idea of processing for our other functions. For rotating the rod, the height depends on the angle. If we feed in pi over 2, the function processes it and produces the number 1. Different angles are processed to give different heights. And the same sort of thing happens with the temperature function. But of course, we have to be careful what we feed into the process. If we go back to the cost function and we try to give it a negative weight, well, we'll just give it indigestion. So we can think of a function as a process, and to describe the function, all we have to do is say what the process does. Well, of course, to do this, first of all, we have to specify the raw materials that the process feeds on. In this case, we've already seen that it doesn't make sense to feed in negative weights. Well, it's easy enough to overcome sloppiness in the definition in examples like this. But in more mathematical contexts, we have to be quite precise about our raw materials, the things that the process operates on. And to help us, we give it a name. We call it the domain. So the domain of a function is just a set of things that the function can process. Now, in this case, the domain is just going to be the set of weights allowed by the post office. Well, that's our input. We also have an output, and we give that a name too. A set containing all the possible outputs from our function we call the codomain. And in this case, the codomain will be some set containing all the possible costs of postage. So in this case, I could have taken for the codomain, well, the set of all positive numbers, or even the set of all numbers, anything, so long as it contains all the outputs. Well, let's have a look at our other functions. This is the rotating rod example. And what's the domain going to be in this case? Well, it's just going to be all the possible angles. And the codomain? Well, this function processes angles and gives heights. So any set containing all the heights will do as our codomain. Let's have a look at our last example. Well, the domain in this case will just be temperatures in degrees Fahrenheit. And the codomain, well, we can take for that temperatures in degrees centigrade. So we see that a function really consists of three things. We have a domain, some sort of process, and a codomain. And we've seen that the domain and the codomain are just sets of objects. They may be numbers, weights, costs, all sorts of possibilities. So now let's concentrate upon this process. Well, of course, it's some sort of rule that connects the domain to the codomain. This rule can take all sorts of forms, but one particularly nice form is when we can actually find a formula connecting domain to codomain. Let me show you what I mean in this case. Now, we know that at freezing point, we have 32 degrees Fahrenheit, and that converts to 0 degrees centigrade. At boiling point, the temperature will be 212 degrees. And in centigrade, that becomes 100. But what about 65? And what about 98.4? That's body temperature. What does that convert to in degrees centigrade? Well, to answer questions like that, we really have to look inside this box, discover what the rule is so that we can apply it ourselves. That means we're going to prise open the lid of this box, look inside, and try and understand just what makes it tick. Inside this box is the rule: subtract 32, divide by 9, multiply by 5. If a temperature arrives in degrees Fahrenheit, the rule tells us what to do. Start with 68, subtract 32, divide by 9, multiply by 5. And that's the result in degrees centigrade. And if the temperature in Fahrenheit was expressed as a symbol T, we'd get the answer in centigrade as 5/9 multiplied by T minus 32. We write that in this way. T goes to 5/9 multiplied by T minus 32. Now we can use this formula as our rule. The rules for our other functions aren't quite so straightforward. The cost of a letter function has a rule given in several different parts. If an input arrives from the domain, it has to be checked against the list to find the corresponding price. What about the height function? The rod is 1 unit long, so when it's rotated through an angle alpha, the height of the end point will be sine alpha. But how can we work out sine alpha? We could use a calculator or a computer, or we could even use a table of values. If an input arrives from the domain, it's checked against the table to find the corresponding answer. The table is just pairs of numbers. The first is input from the domain, the second is the output to the codomain. In this case, the answer is approximate because the table has only 3 decimal places, and because you might have an input that isn't actually in the table. So you have to take the nearest value or approximate in some other way. But in principle, such a table could be made as accurate as we liked. So that's one way of representing functions. But as this course progresses, we're going to make repeated use of a way of representing functions pictorially. Now, this is a useful thing to do because it's often easier to assimilate a picture rather than, say, tables of numbers. Well, let me show you using this temperature conversion function. Now, freezing point is 32 degrees Fahrenheit, and that goes to 0 degrees centigrade. So I can represent that by using this arrow. You may remember we did something similar in the last television program when we talked about transformations. Well, now what happens if the temperature rises to boiling point, 212 degrees Fahrenheit? As we'd expect, the corresponding temperature in centigrade is 100, and I can represent that by this arrow. Let's try one other temperature. In this case, this temperature in Fahrenheit goes to this temperature down here in centigrade. Another arrow. So there we are. I've represented my function as a picture. But of course the trouble with this is if I keep throwing in arrows like this, it won't be very long before the picture is very messy. And anyhow, it doesn't really give me a feel for what's going on. Well, all is not lost. I can be rather cunning. I can use my input and my output as coordinates of a point. Here, 32 degrees goes to 0 degrees centigrade. So I can use the 32 as the x coordinate and the 0 as a y coordinate of a point. I'll just get this point. Let's try it at another point. Well, this temperature in degrees Fahrenheit goes to this in degrees centigrade. I can use this as the x coordinate This is the y coordinate, and I'll just get this point. Let's do it once more. In this case, the point I'm going to get will just be here. Well, now, of course, I couldn't do this for every single point, but if I could, what I'd get would be this straight line. And the collection of all these points, this straight line, we call the graph of the function. Now, of course, I can draw graphs of lots of different functions. For example, the function representing the cost of posting a letter looks quite different to this one. Well, this is our third function, and I find the graph in this case rather fascinating. As the rod rotates, the point moves on a circular path. We want to plot the height of the point above the axis. We can concentrate on the height by viewing the circle edge on. Although, of course, when we do this, we lose sight of the angle. Anyhow, we want to write that angle along the x-axis. And now the graph looks like this. So here we have the graphs of our three functions, and I think you can begin to see why I say drawing pictures is such a useful thing to do. For example, take the sine function. From its graph, we can see immediately that the values of the sine function lie between plus and minus 1. And we can compare this with this straight line graph. Just from the graph, we know that the functions must be quite different. And because this is a straight line, we know that as degrees Fahrenheit increase, so degrees centigrade must increase. And both these are quite different from the graph we get for the function representing the cost of posting a letter. So you see that by drawing the graph of functions, often properties of the functions just leap out at you.
Well, we've come quite a long way, really. We've seen that a function has essentially three ingredients. There's a domain, a rule, and a codomain. Every object in the domain is processed by the rule to give you something in the codomain. Now, one reason why mathematicians like to define functions in such a precise way is that it packages together a whole lot of information, and then you can regard the function as an object in itself to be manipulated. And if you give the function, say, a symbol, a label, supposing we gave this a symbol f to stand for that function, then we might be able to find ways of manipulating symbols like that, and thus manipulating a whole batch of information. Now, in the text, you'll see a lot of ways of combining functions, and many of them are very similar to ordinary arithmetic. But there is one way which is so special to the very nature of function that I'd like to show you some more about it. Look back at this example, temperature conversion. Really, the rule here tells you to do two things. First of all, you have to subtract 32. Then you have to multiply by 5/9. So, for example, 50 first becomes 18, and then that becomes 10. Now you see we've got two functions, and I can give those labels. If I call that one G and that one H, can you see what's going on? If I apply the function G first and then H, I'm combining them to give me the function f. We say that the function f is the composition of the two simple functions. Now I'd like to give you another example of composition that's a bit more complicated. Not just because it is complicated, but because it is an example of using rules, manipulating symbols. That's just the sort of thing you're going to have to be able to do. It's to do with photography. I don't know if you know, but when you're developing film, the time for development depends on the temperature of the room. The word depend suggests there's a function around, and there is. And we can draw its graph. The manufacturers tell us that if the temperature is 20 degrees centigrade, you've got to develop for 8 minutes. And for every degree above 20, you have to reduce the time for developing by 1/6 of a minute. And here's the rule for developing time. Now, if you take the domain and the codomain for that rule as being all real numbers, you get the complete straight line. And the developing time and temperature are not related all the way along that line. But under normal operating conditions, then it's a pretty good approximation. Problem is that usually you've got temperatures in your darkroom in Fahrenheit degrees rather than centigrade. And that's where composition comes in. Here's our developing time rule. Here's our temperature conversion rule. If I first apply that rule and then apply that rule, the total effect, the composition, will be developing time in terms of degrees Fahrenheit. What I'd like is a rule for that composition function. How do I get it? Look at this thing a bit more closely. What does it tell you? It tells me whatever I take, I have to subtract 20, multiply by -1/6, and then add 8. And what I take is x, the input. But now I want the input not to be x, but the output from here, which is 5/9 of t minus 32. Now I worked all that lot out before the program, and it comes to -5/54 times t minus 68, add 8. That's an expression in T. It's my developing time in terms of temperature in degrees Fahrenheit. That's my rule for the composite function. Well, don't worry too much about the details of that calculation. You'll get plenty of chance for practice in the text. But remember the principles. What you do is take the output from the first function and plug that directly into the formula for the second function, for the rule for the second function. You'll get plenty of practice at doing that. You'll also see in the text the other ways of combining functions. So, until next time, goodbye.